Hello everyone, my name is Lydia Perovic and I am PhD in food technology, currently working as a research assistant at Institute of Food Technology from University of Novi Sad, Serbia. The topic of my research that I'm going to show you today is the valorization of sugar beet pulp as an effective biosorbent for entrapping metal ions. So it is my great pleasure to have this precious opportunity to be part of the project named Agri-food Waste Management for Sustainable Bioeconomy through higher education, curricula, and upskilling. And the goals of this project, named AGRIMA shortly, is fostering universities' capacity building for the green transition through innovative practices and higher education curricula updating in agri-food waste management for the circular bioeconomy. Here is represented all the partners of this project, and among all of these partners, one of them is University of Novi Sad, from which I'm coming. As I previously mentioned, I am from Institute of Food Technology, short named FINS, which is part of the University of Novi Sad. University of Novi Sad is the second largest university in Serbia after the Belgrade University, and Belgrade is our capital city of the Republic of Serbia. University of Novi Sad consists of 14 faculties and 3 institutes, among which one is FINS, which is located here at the beginning of the University of Novi Sad campus. My institute is organized in 3 research centers. First one is a research center for food safety and chemistry, and I'm part of this research center. Other one is the research center for food technologies and product development, whereas the third research center is for technology, quality, and safety of animal feed. Also, within our institute, we have accredited laboratory. We did the analysis for food producers and for everyone who bring to us some food product, and also one part is corresponds to administrative workers. But currently, we have 67 researchers employed at Institute of Food Technology. FINS is dedicated to enlarging international cooperation worldwide for sustainable future in science. Also, one of the main focuses are innovative topics work, and we want to increase our visibility and recognition through active publication and active participation for various projects. And the last decade of science is focused on transfer technology, which means better commercialization of our research and entering the research market. We are funded by domestic ministries. Mostly, one part is funded by provincial secretariats, and we got some funds in Serbia. Also, it is necessary to mention the funds from European Union. Our long-term strategy is to improve internal existing capacities, to increase scientific excellence, and advance commercialization of our scientific results. And I will finish with this slide, the short introduction about my institute. So last year was organized the Food Tech Congress, which we have planned to organize every 2 years. So in 2026 will be probably our next Food Tech Congress. So everybody is invited to join us in Novi Sad. And also our institute has one journal where you can publish twice every year. So now I will continue with our today's topic, which is, as I previously mentioned, polarization of sugar beet pulp as an effective biosorbent for entrapping metal ions. Since we are witnesses and contemporaries of a production consumer society in which the awareness of the possibilities of maximum utilization of certain material and energy flows is not sufficiently developed. The primary goal that we want to achieve with this research is to transform the linear economy into a circular economy by reducing the large amount of accumulated bio-waste. The main disadvantage of the linear economy is the use of the large amount of non-renewable fossil fuels, while with the circular economy, raw materials are reused, change their function, and can be turned into functional component. Something that is primarily secondary product, such as sugar beet pulp in my research, and does not have high production values, become indispensable component of the primary process through valorization and has therefore an increased value. Using biowaste, we can satisfy two concepts. First, concept of zero waste technology and the circular economy. So I will start with the sugar production system and show you the technological units that are really precisely connected in one whole unit. So the technology of sugar production is energetically demanding process that consists of large number of technological operations synergistically connected in one whole unit. First, the sugar beet pulp we can see is washed, then cut in a loop-shaped noodles, after which it meets the extraction station with water in the extractors, after which the noodles and the juice are separated. As a product of this phase, we got the extraction juice, which is the starting juice of the juice purification stage, which is shown here. I will focus in this research in improving the juice purification stage with adding some additional purification technology in order to improve the whole juice purification process, to improve it and to get more sugar at the end. As I mentioned, the starting juice of the juice purification stage is extraction juice. After one step of alkalization and carbonation, we obtain the alkalization juice, which is the intermediate product of juice purification stage. And the final product of the juice purification stage is thin juice. Thin juice, afterwards, we go to evaporation station, becomes thicker, and at the centrifuges, we got the primary product of sugar industry, which is crystal sugar, and the main byproduct is molasses. So the whole goal of the sugar industry is to get as much as possible sugar and to leave as less as possible sugar in molasses. So the phase of thin juice purification is the most important stage in the production of sugar, since the efficiency and utilization of the entire sugar factory depends on its success. They call the juice purification stage as heart of the sugar industry. The goal of thin juice purification station is to remove all non-sugar components from the alkali juice, therefore increasing its purity by mechanical process purification, which means filtration, and chemical purification, which means alkalization and carbonatation. So the main goal of the purification stage is to improve purity of juices by increasing amount of sugar on dry matter substance. Alkali juice, as an intermediate product of the thin juice purification process, has temperature around 70 to 80 degrees, and the natural pH value of this alkalized juice is 10.5. While the proportion of color substances, we can see from the table, is significantly lower than in the extraction juice, and it already has high purity quotient, which means that from the 15 to 16% of the dry matter that alkali juice have, around 90% is dedicated to just sucrose, but we have also 10%, which is some other particles. So, alkali juice is multi-component system which has dissolved sugar inside and also other non-sugar particles. What are the non-sugar or non-sucrose substances? Non-sucrose substances in sugar industry are all other substances except crystal sugar. So all components except the crystal sugars are referred as non-sucrose substances. And the goal of the purification is to reduce their presence to the smallest possible share, since they cause the formation of scales on the preparation bodies, they increase the solubility of the sucrose, and also lead process to loss in molasses. The higher their share, the more purity corrections agents are used, and therefore workability of the juice is more difficult. So the main goal is to reduce these non-sugar substances in alkali juice and as much as possible. So, of the also non-sucrose substances present in alkali juice, in this research, the emphasis is on the molasses-forming metal ions. They reach the sugar beet through the root system from the ground, and they are present naturally in the sugar beet in around 0.4 to 0.6%. During the extraction, together with sugar, these non-sucrose substances also end up in the juice, and in the extraction juice, they are present in 0.4 percentage. As the juice purification stage goes further, when we got the tin juice, there is 0.2 amount of these molybdenogenic metal ions, and each of them has different capacity for molasses forming, and the highest molasses forming quotient has the potassium. So the main idea of this research is to use the byproducts from the sugar industry, for example, sugar beet pulp, in the form of biosorbent to entrap that molassigenic metal ions, and to make this tin juice or alkali juice more pure. So to reduce the content of metal ions in alkali juice, byproducts of the sugar industry were used, which represents lignocellulosic materials, in 1/3 of which are represented by cellulose, hemicellulose, and pectin, whereas lignin is consisted in a bit smaller amount. So the three types of byproducts from sugar industry are used in this research, and they are separated in three groups. First, dry. Among dry byproducts, we use dry extracted sugar beet pulp, sugarcane fibers. Among wet byproducts, we use wet pressed extracted sugar beet pulp, and we try to modify the dry extracted sugar beet pulp. So that's the fourth type of the byproduct that we use in current research. And here the adsorption like singled out as a solution. Adsorption process represents the process of accumulation of substances on the boundary surface between two phases. In our case, we have a liquid-solid adsorption. Liquid is alkali juice, and the solid is our biosorbent sugar beet pulp. And where the adsorbent is, they are said is in solid aggregate state, and the molasses forming metals are adsorbate. We see here on the picture the orange circles, which are entrapped in that holes here on the adsorbent, which is sugar beet pulp in our case. When we use some biological matrix, something from the biological origin, we change the topic from adsorbent to biosorbent. So biosorption is type of adsorption where the biological matrix is used as an adsorbent. In this case, byproduct of the sugar industry. There are numerous of benefits using a biological matrix in the form of adsorbent, such as their availability, high availability, low purchase price, reduction of the accumulation of the bio-waste, and also non-toxicity, since the biosorbent is naturally obtained during sugar production process. And I use two different type of biosorption. Discontinuous biosorption as simpler process, and continuous biosorption. Within this continuous biosorption, we have batch system where the alkali juice and sugar beet pulp are constantly shaking, and we have the constant amount of alkali juice and sugar beet pulp. Other type of discontinuous biosorption is closed loop system. We also have here constant amount of alkali juice and sugar beet pulp, which is located in the biosorption column. But here we have constant circulation of the alkali juice through the biosorbent. And the third one, the continuous procedure, means that we don't have the constant ratio of the alkali juice and sugar beet pulp. Alkali juice goes through the biosorbent fixed beds of the biosorbent in the column, and we take some aliquots of the alkali juice after it passed through the biosorbent. And the end of the biosorption process is when the amount of molossigenic metal ions in effluent are the same as in the influent. That means that process is done and the biosorbent is completely saturated, the whole free spots, free places for molossigenic metal ions entrapping, catching, or ion exchange is fulfilled. Then the biosorption process is done. So this apparatus that I show you here, we create by ourselves on my institute in cooperation with Faculty of Technology, and we patented this procedure and also the apparatus and the whole procedure of the biosorption of alkaline and of the molossigenic metal ions from the alkali juice with non-modified pressed extracted sugar beet pulp, and that patent is on national level. So sugar beet pulp has various purposes, but during this lecture, I'll talk to you about the valorization of sugar beet pulp in four of the biosorbent. But we must mention other purposes of the sugar beet pulp. For example, as sugar beet pulp take crucial place in the fermentation processes. Also, we can get the bioethanol, biogas from the sugar beet pulp. Also, one of the most important and since few decades ago, the only way we use the sugar beet pulp after the sugar beet process is for animal feeding. And also sugar beet pulp is a good fertilizer for soil. We use it as a compost. But since few years ago or 1 decade ago, we find out that sugar beet pulp has some adsorptive characteristics and can be used as a biosorbent. At the beginning of my research, I checked the chemical composition of the biosorbents that I mentioned that I will use, also physical chemical properties, sorption properties, and I represent here the results. Only sugar beet pulp, the wet pressed extracted sugar beet pulp, has a really low dry matter, which means that on this byproduct is not they are not dried and not additional technological operation is used, which is from the economical point of view better. So you don't need to dry additionally the sugar beet pulp, which is obtained in sugar industry. You can directly use it in the way which is obtained in sugar beet pulp, which is obtained in the sugar industry, and therefore there are lower economical costs for their obtaining. Also, the wet pressed extracted sugar beet pulp has the highest amount of the proteins on dry matter, but all of them have the really high amount, of more than 70% of the fibers in their structure, and high proportion of protein in pressed sugar beet pulp resulted in better surface properties and surface activity of sugar beet pulp, which is really important for absorption process. And due to extremely high proportion of fibers in sugar beet pulp, they have good hydration properties, which is also important for the removal of the most organic metal ions in the bioabsorption column, and we see that this sugar beet pulp already has some most organic metal ions in their composition, which means some of the active sites for the bioabsorption removal, it's already there's some metals already over there, but there's still enough free spaces for additional removal of most organic metal ions. Previously characterized byproducts of the sugar industry were used in a preliminary study to find the most effective one biosorbent in terms of metal ions removal efficiency. And determining the efficiency, biosorbent selecting the most effective one was the wet pressed extracted sugar beet pulp, which removed these most organic metal ions from the alkali juice in the highest ratio. And the experiment conditions was natural temperature and pH value of the alkali juice, and this research was done in the batch conditions of the biosorption. After we choose the best one biosorbent, we checked all the absorption characteristics that wet press extracted sugar beet pulp had. First, we checked the thermogravimetric features. Also, the zero point of charge is important factor. Amount of acid and base groups on the biosorbent surface, porosity and specific surface. We check the functional groups and chemical bonds present on the surface of the biosorbent and their morphological structure. So from the thermographs represented as a diagram of the dependence of thermal decomposition, which means weight loss, of the sample depending on time due to increase in temperature. So here are two diagrams of the dependence of the mass change of pressed extracted sugar beet pulp before and after the biosorption procedure obtained during a non-isothermal process with temperature increase step of 5 degrees per minute in nitrogen atmosphere. The dependence of the change of the first derivative of mass loss over time with temperature are shown on the second graph. So each peak symbolizes the exothermic process. We see from diagram the hemicellulose is the least stable with peak at 150 degrees. After that, the cellulose is decomposed in a pretty much wider range from 200 to 450, whereas lignin is the most stable compound of the sugar beet pulp, which is referred to the complex structure that lignin has, complex amorphous structure with three-dimensional polymers consisting of three different types of phenyl propanol units, such as p-hydroxyphenyl, guanyl, and syringyl. And these three units are degraded over a very wide range. And we see on the first graph that after 500 degrees of Celsius, the whole sugar beet pulp is completely destroyed. And after 500, we got the ash. So the pH value, if we talk about pH value, this is one of the key factors influencing the biosorption process. In order to be able to define the mechanism by which ion exchange takes place between the biosorbent and the liquid that contains metal ions, which is in our case alkali juice, it is really necessary to know at which pH value the biosorbent has 0 point of electricity, is not electrified, and we got there as a result that the pH value is of the 0 point charge is 5.9. In all pH values above the pH value of 0 point charge, the surface of the biosorbent is negatively charged, which is important because we did the whole experiments in alkaline conditions, and when we want to remove the positively charged monoorganic metal ions, it is really good to have the difference in the ionization. And with help of the Bohemian titration techniques, we determine the presence of acidic and base groups on the surface of biosorbent. We see that it has much more acid groups on the surface, which is also good. And among them, the carboxylic groups are one, which is uh, the most represented for the biosorption for the process of biosorption, and it takes the main role in the biosorption procedure, and because of the numerous galacturonic residues from the pectin units of the sugar beet pulp. Also, we suspected that the one mechanism with which we remove molluscogenic metal ions are ion exchange. The other one is the precipitation or simpler entrapping of the molluscogenic metal ions in the pores of the sugar beet pulp. The total porosity of the pressed extracted sugar beet pulp is 53%, determined by intrusion porosimetry. And with the pores, which has the pores with a share higher of 50 nanometers, presently 60.55%, which declares this biosorbent due to UPAC nomenclature as a macroporous. And the specific surface area of the sugar beet pulp is 0.9 square meters per gram. Comparing to active carbon, for example, which is also one of the most important, one of the most known adsorbent, it has a specific surface around 300 square meters per gram. So this is a really small specific surface, but if we talk about lignocellulosic natural material, that is in a correlation with literature one's data. And other analysis that we conduct is the presence of the functional group on the surface of the sugar beet pulp. And we did that with Fourier transformation of the infrared spectroscopy. The principle of method is based on the movement of atoms inside the biomolecules, and the measured materials is irradiated with rays of the infrared spectrum, but the method itself is not destructive. The first broad peak that we see on this graph, same as for the biosorption procedure, I mean for the sugar beet pulp before and after the biosorption procedure, it appears as 3,200 to 3,500, and which corresponds to the vibration of the hydrogen bonds, stretching groups, typical for the lignocellulosic materials. The next peak corresponds to the aliphatic and alicyclic CH vibrations from the carbon chain of the lignin and hemicellulose. Small peak appears at the 2,300 centimeters and indicates the presence of the C triple bonded groups. Other peak, which appears in 1,700 to 1,800, with a peak in 1,733 centimeters, refers to stretching vibrations of the carbonyl functional group from the aldehyde. And we have series of peaks occurring between 1,300 to 1,364, which is CO groups, and also the last peak refer to COC groups, which is from the beta glucosidic bonds within the sugar present in the sugar units. Also, we want to check the morphological structure using electron microscope with electron dispersed detector. As a result, scanning electron microscopy provided information of the morphology of the biosorbent surface, porosity structure. We see the hollow fibers of cellulose. We see how it changed before and after the biosorption procedure due to really good hydration properties that I mentioned before. We see that they are they're more slightly, the fibers look after the biosorption procedure. And with help of an electronic dispersive detector, we see that the changes of the molassigenic metal ions on the biosorbent surface. We see that the amount of sodium, potassium, and calcium increased on the sugar beet pulp surface, which referred to which is the good agreement with our results. And we can say that they are a bit more amount of these molassigenic metal ions on sugar beet pulp after the biosorption procedure, because the biosorption procedure happens after we in detail check the sorption structure and the sorption properties of the sugar beet pulp. We continue our research with biosorption procedures. First, we did this continuous biosorption in batch system. After that, we did the discontinuous biosorption procedure in closed loop system. And the third procedure was continuous biosorption processes. So we start the batch biosorption, and one of the most important pieces of information when evaluating a new ion exchange biosorbent is time required to reach equilibrium, the kinetics of metal ions binding, as well as the biosorption mechanism itself. The biosorption kinetics and dynamics can be analyzed by applying different kinetics and diffusion models to experimental data. So we did an experiment in the Erlenmeyer task. So the sugar beet pulp and the alkali juice is constantly stirring and mixing on a constant temperature and with constant pH value. As a result, we plotted the diagram where you can see the removal efficiency during the time, how it changed, and equilibrium is reached after 80 minutes from the start of the work, simultaneously for all free metal ions. We see the calcium ions are removed in drastically higher proportion compared to sodium potassium, which indicates that calcium is removed by some additional mechanism, not only by ion exchange. Due to low solubility, it is suspected that calcium is removed by the precipitation mechanism. Mathematical models of the kinetic curves and diffusion curves we applied to the previously obtained experimental results, and we got as a result that the potassium and calcium are removing mostly by the pseudo first kinetic model order, and that means that the reaction is really fast and favored, whereas sodium is removed by the second kinetic order model, which means that the dominant mechanism is ion exchange and chemisorption. If we consider the Weber-Morris interparticle diffusion model, which indicates that we have multilinearity of the system, we can see like the two linear phases in the Weber-Morris, the purple line, the interparticle diffusion model, which means that we have the internal and external diffusion of the metals in the sugar beet pulp's pores. After that, we did the isotherm studies. Isotherms show the mode of the interaction of the metal ions and biosorbents and provide some basic information about the biosorption process. We see that potassium and sodium are removing based on the Langmuir isotherm model, and which means that these monovalent ions are removing in the monolayer on the biosorbent, whereas calcium as the bivalent molecule atom is removing in more layers, not only one layer. And if the results are in the correlation with Freundlich isotherm models, we know that the surface of the biosorbent is heterogeneous. So after we finished with basic analysis with the batch biosorption procedure, we continue with closed loop biosorption system. With this apparatus, we want to optimize some biosorption parameters. First, we vary the parameter of temperature on the free levels, pH value of alkali juice, and volume of alkali juice. The dependent variables that we are considering is removal efficiency of sodium, potassium, and calcium. Also, one really important parameter is sucrose level. So this bioabsorption procedure is considered as an additional purification procedure that we want to add to the standard unit operations. And if you want to add some additional procedure, the most important factor is not to reduce the amount of the final product, which is sucrose. So it is really important to follow if the sucrose level is not reducing. After plotting the 23 experiments in 3 diagrams, where we see on the y-axis the removal efficiency of molassigenic metal ions, whereas on the x-axis are the parameters varied on 3 levels. And we see that on table shown down, that the calcium is also with this procedure is removed like 2 times better than when we have the batch conditions, which are not optimized. With optimized closed loop system equipment, we have pretty much high removal efficiency of these molassigenic metal ions, but calcium is removed in a pretty much higher percentage than as monovalent sodium and potassium. When we talk about the sodium and potassium from the graphs, we see that with the increase in pH value, the efficiency of metal ion removal increases to the medium value. With the increase in temperature, the efficiency of the removing metal ions also increases because of the greater solubility of the ions with a higher temperature and the concentration gradient that prevails, the boundaries decreases. The increase in volume had a negative effect on the removal efficiency of the metal ions, considering sodium and potassium. Which means there is no additional mechanism for the removal of the sodium potassium. And when we have the higher volume of liquid, it faster filled the empty spaces, the active sites on the biosorbent. So it's always better removal efficiency when we have less liquid to purify with the same amount of the sugar beet pulp. And when we consider the third graph of the calcium, pH affects the distribution of cations on the surface of biomaterials. With increase in pH value and temperature, calcium removal efficiency is gradually increasing. pH affects strong conformational changes in the chains of the pectin of the sugar beet pulp, and which is polyelectrolyte, and rise in temperature affects the viscosity and the fluidity of the alkali juice. Higher temperature affects better mobility of the alkali juice, and synergistic effect of temperature and alkali juice affects the precipitation of calcium ions. So there is the reason why we have better removal of calcium ions, because it is removed by 2 mechanisms. Here is represented the suspected bioabsorption mechanism. So we see the hydrogen ions from the carboxylic groups is replacing the hydrogen with the monovalent sodium and potassium, whereas calcium, because it is a bivalent metal ion, it creates the bridges between 2 polygalacturonic units of the pectin, and it also affects some conformational changes. After the discontinuous procedure, we continue with continuous bioabsorption. We did the same type of the central composite design experiment. We worried the filling height of the biosorbent, flow of the alkali juice, and the granulation, which means the particles of the sugar beet pulp. As dependent variables, we consider removal efficiency of molassigenic metal ions. And we see with this procedure of the biosorption, we got the highest removal efficiency since the beginning of our research. As more as we optimize our biosorption procedure, and we got the high removal efficiency, and that is really good that we got the highest removal efficiency with continuous biosorption, which is really good for the scaling up of the system and coming closer to the industrial conditions. Here is shown the breakthrough curves obtained during the continuous biosorption. On the first graph, we make the filling height, bed height of the sugar beet pulp and the granulation constant, and we see how the changes in flow affected the obtaining the breakthrough time and the saturation of the sugar beet pulp. On the second graph, we make the constant of the flow and the granulation and check how the bed level height influenced the trend of the removal efficiency of the sugar beet pulp. And on the third graph, we fix the flow rate and the bed level height and see if the changes in granulation affected somehow the removal efficiency. From the first graph, we see that from 25 to 12 minutes, breakthrough point decreased when the flow rate increased. At higher flow rate, mass transfer is enhanced. Ions are shorter retented in the column, and curve is steeper. At higher flow rate, shorter saturation shorter saturation time, and when the flow rate is lower, there is present also an external diffusion, and same we have there is time for internal diffusion, and therefore the more metal ions are removed. The different mass of the biosorbent on the second graph affects the different filling height in the column. Sharper curve was shown at the lower filling height, and there is smaller specific surface active sites at lower filling height. Higher filling height can offer the bigger transfer zone for the metal ions, which is better for the biosorption removal efficiency. And on the third graph, the greater granulation, the specific surface area of the biosorbent is smaller. And with smaller particles, there is a greater influence of intraparticle diffusion process. But we see that because we didn't grind the sugar beet pulp, we just separated in three different ratios among according to size. That means that external surface didn't influence so much our results. If we maybe grind that to the smaller particles, smaller than 1 centimeters, maybe it will be the greater influence on the final results. Here we can see as we optimize much more our biosorption procedure, we got the better removal efficiency. Considering sugar content, it is necessary to mention that that amount of sugar content in the alkali juice stayed unchanged. Doesn't matter which process we use, but with optimizing the parameters of the biosorption, we got the higher removal efficiency of our metal ions. After the biosorption process is done, we can consider what to do with sugar beet pulp, which is enriched in monosorganic metal ions. Monosorganic metal ions are sodium, potassium, and calcium, which are not heavy metals, and you can easily use this sugar beet pulp after the biosorption procedure as a ruminant feed with increased mineral composition. But that is the one case. If you want to use the sugar beet pulp for other biosorption process, you can continue with biosorption desorption process like one cycle and continue as much as the sugar beet pulp shows the removal efficiency properties. So we try to remove the entrapped monosorganic metal ions from the sugar beet pulp, and when we are considering the most effective desorption agent, we are considering also the least invasive one, and the nitrogen hydrogen acid showed as the best one with the highest highest desorption efficiency of all three molluscigenic metals and with the least destroyed sugar beet pulp. So to conclude, the most effective biosorbent from the sugar beet industry is wet pressed extracted sugar beet pulp, which are macroporous. The main functional groups responsible for ion exchange for entrapping the process of the molluscigenic metal ions are hydroxyl and carboxyl functional groups originating for polygalacturonics residues of the sugar beet pectin. The alkali juice at its native temperature and pH value show the higher removal efficiency of the calcium ions as bivalent metal ions than monovalent cations, but the equilibrium are obtained at the same moment for all three of them. The calcium is removed with the highest removal efficiency during the closed loop system when the temperature and the pH value is 70 degrees and 12.5, whereas sodium and potassiums are better removed on the medium conditions and medium level of parameters, which is 50 degrees and 10.5 pH value. In the continuous biosorption, we see that the better filling height is better for greater filling height of the biosorbent in the column is better for higher removal efficiency, and also the lower juice flow rate enables better external and internal diffusion process of the metal ions in the sugar beet pulp. And we see that monovalent cations are removed just by iosorption and chemisorption process, while poorly soluble calcium ions are removed also with additional process with precipitation. And as I said, this pressed sugar beet pulp, this process is really eco-friendly because after the biosorption process, it doesn't have the heavy metals. This biosorbent sugar beet pulp is used for removal of macro components, and it looks like a better food for animals after biosorption process. It is not harmful to destroy sugar beet pulp somewhere, but you can also use a desorption process or to close the circle and give this biosorbent with molluscigenic metal ions to the animals. And that will be all for now. Thank you very much for your attention. Don't hesitate to ask me if you have any questions regarding this topic or whichever other topic. I'm open for the questions and open to communication and to further cooperation. Here is my email. So if you have any questions, you ask me, and I will be very happy to help you or to discuss with you about this topic. Thank you and see you.